Boom. All right, Julie, welcome back to the last chapter, and that is nuclear chemistry, aka radioactivity. Yeah, nuclear chemistry. This is the last chapter of this amazing course, Chem 111, and it happens to be modern physics, where you talk about different stuffs like radioactive substances, artificial substance, naturally occurring substances, stuffs like that. So let's go into it. Let's see what this amazing topic has for us. So, nuclear chemistry. Nuclear chemistry is a branch of chemistry that deals with the study of atoms that experiences changes in their nucleus, right? So it deals with it's a branch of chemistry that deals with atoms that experiences change in their nucleus. And this change usually comes in spontaneously. Nobody catalyzes it. You don't need heat, you don't need pressure, you don't need temperature for a change to occur inside the nucleus of the atom. So that branch of chemistry whereby changes occur spontaneously inside the nucleus of an atom, that you refer to as nuclear chemistry. Okay, now these substances that actually experience change in their nucleus are called radioactive substances. There are basically two types of radioactive substances. Number one, the natural radioactive substances, and then two, the artificial radioactive substances. Natural radioactive substances, as the name implies, they occur freely in nature. Typical examples are uranium-238, uranium-235, thorium-234, and natural radioactive substances. They are natural. Nobody created them. We came to find them on planet Earth. But substances like organosine, moscovium, flavorium, no, flerovium, those guys are actually artificial because they were created by man, okay? So artificial radioactive substances are those substances made by man through the bombardment of non-radioactive substances using particles to create radioactive substances. That means bombarding a non-radioactive substance using an alpha particle or a beta particle to produce an artificial radioactive substance. That is what we call artificial radioactivity. And a typical example of such is the formation of organosine. Right? It's important for you to note that most radioactive substances in the periodic table starts from atomic number 83 to 118. They are all artificially made. That 83 is bismuth. From bismuth to organosine are artificially made. So you find a natural substance like carbon being bombarded with californium in the presence of about 250 million electron volt worth of energy to produce 3 neutrons and a mysterious element called organosine, which is an artificial compound. So that is artificial radioactivity. Bombarding a naturally occurring substance with a particle to form artificial substances. That is artificial radioactivity. So let's go into a brief history of radioactivity. How did radioactivity come into play? What brought about radioactivity? Now, the father of radioactivity is Henry Becquerel, who founded uranium stone on his way, probably going for a lecture to go and teach his class, and decided to wrap this uranium stone because the stone looked bizarre to him. So he wrapped the stone into a foil and kept it in a cupboard. Few days later, he noticed that the stone was emitting some kind of radiations he had no idea about. Maria Curie, which happens to be a PhD student of his, also isolated some few similar stones. She isolated radium, she isolated polonium. In fact, she named it polonium because she was born in Poland. So she said, I will name this substance polonium. Until today, we call it polonium. And polonium happens to be a metalloid in the periodic table, So she isolated polonium also. And when she came in contact with her lecturer, Henry Becquerel, and also expressed her, her surprise about these elements, and they were like, I too isolated some elements like this. So why do we call this type of elements that actually spontaneously emit radiation on their own without anybody causing it to happen? So she decided to suggest the name radioactive substances. Let's call them radioactive substances. In other words, they are radioactive in nature. They emit substances spontaneously without anybody catalyzing the effect from happening. And that led to the birth of what we call radioactivity. And the big question now is, what is radioactivity? It is the spontaneous disintegration of the nucleus of an element to emit radiation spontaneously without being catalyzed by anything. That is radioactivity. The spontaneous disintegration of the nucleus of an element to emit radiation spontaneously without anything catalyzing it, without pressure, without temperature, without anything at all. That is radioactivity. And that brings us to the particles being emitted. There are basically 4 particles emitted. Basically 4 particles emitted by radioactive substances, which are number 1, alpha particle, number 2, beta particle, number 3, gamma ray, number 4, X-ray. Yes, X-ray is one of the particles, okay? So don't just think that there are just 3. There are 4 of them in number. Alpha, beta, gamma, and X-ray. Alpha particles have helium nuclei. Beta particles are of 2 types. We have the positron and the negatron. As for the gamma, it has no charge. It's 0, 0. Now, in radioactivity, when you see an element, at the top left of the element is always the charge, okay? While at the, sorry, did I say the charge? Yes, it should be the charge. While at the bottom is always the mass. Am I sure? No, the reverse is the case. At the top left is the mass, while at the bottom left is the charge, okay? Always use electron to remember. Electron, for example, has no mass. So it is 0 at the top, but minus at the bottom, isn't it? A neutron, for example, a neutron particle, for example, is heavy. It has no charge. It is 0 at the bottom and 1 at the top. You get it? All right. So basically that is that. Now, among these 4 particles being emitted by radioactive substances, ionization energy is highest in the heaviest particle, which is the alpha particle that has a mass of 4 AMU. Ionization energy is heaviest or highest in it and lowest in X-ray. Yes, it's lowest in X-ray. Now, as for the penetrating power is highest in gamma ray. Penetrating power is highest in gamma ray and lowest in alpha particle, and you can see that in the electromagnetic spectrum. Okay, good. So that takes us to what instrument can you use, or let me just put it this way. These radiations, which are the alpha particle, beta particle, gamma rays, and then X-ray, are however detectable by the use of the following instrument. In other words, what kind of instrument can you use to detect an alpha particle, a gamma particle, a gamma ray, or an X-ray? The first one here is the Geiger-Moller counter. Geiger-Moller counter. The second is the scintillation counter. The third is the electron cloud chamber. And then the fourth is the spinthariscope. Let me call it the spinthariscope. Spinthariscope. Those names are a little bit awkward, but just remember them just for the sake of education. So that takes us to the next part, which is called the K-capture. Now, what do we mean by E-capture? It's actually E-capture, though E-capture is also called a K-capture. E-capture is a phenomenon that occurs when the nucleus of an atom captures an electron, captures or attracts an electron into its nucleus, into itself. However, this leads to a decrease in the charge of the nucleus. When a nucleus attracts an electron to itself, remember inside the nucleus you have protons and neutrons. So when it attracts an electron to itself that is negatively charged, that electron that is negatively charged will counterbalance one of the protons in the nucleus. So there will be a decrease in the charge of the nucleus. And when that happens, that proton that will be sacrificed by the incoming electron will form what we call a positron. So it's a new particle form called the positron. Very, very important. So you have to understand this very well. That is positron formation. So E-capture is also referred to as positron emission or K-capture. Why K-capture? Because the electron being captured inside the nucleus is coming from the K shell. And it's also important for you to know that each time an electron is being captured into the nucleus from the K shell, an electron in the L shell will have to jump back to the K shell. As the electron from the L shell jumps back to the K shell, another electron from the M shell will jump back to replace the one that left from the L shell. So it will continue to jump like that, like that, like that. And the good thing that happens there is, as soon as this electron jumps back to replace the captured electron, it emits a radiation called X-ray. And the X-ray being emitted is highly energetic, and it's important for you to know that the ray emitted here called X-ray has an energy potential equal to the difference between the energies of the captured electron and the replacing electron. And of course, this ray was discovered by Roentgen, Roentgen. We've discussed that. And at times, he even tempted to call it the Roentgen ray, as the case may be. So if you look, for example, a reaction that can lead to the formation of an X-ray, for example, you have barium 56 plus an electron to give you caesium 55 plus an X-ray. That's a radioactive reaction. Nota bene, a positron is formed when a proton changes to a neutron. And for a proton to change to a neutron, that means an electron has been captured. While a negatron is formed when a neutron changes to a proton. That forms a negatron. So for you to get a positron, all you need to do is to have a change from a proton to a neutron. And that would lead to the formation of a positron. So you're going to have 0 and plus at the bottom of B. It's called positron. So you have proton giving you neutron and positron. But when a neutron changes to a proton, it gives you a negatron. A negatron. That means 0 and minus 1 at the bottom of the B. You get it? All right. So that takes us to the next part, which is called radioactive decay. What is radioactive decay? This is the substance, or let me say, this is the spontaneous disintegration of the nucleus of a substance. Yes. Radioactive decay is the spontaneous disintegration of the nucleus of a substance, leading to the emission of either a beta particle, an alpha particle, or both of them. No radioactive substance can emit all 3 radiations or all 4 radiations at the same time. When a substance emits an alpha particle, it is referred to as an alpha decay. And when a substance emits a beta particle, it is referred to as a beta decay. For example, uranium-238, of course, uranium has an atomic number of 92. Uranium-238 actually will decay into thorium-234, atomic number of 90, through an alpha decay, okay? While thorium will decay into potassium. Potassium is 234, atomic number 91, that's Pa, through a beta decay. And then you have that E with 0 and minus 1 at the bottom. So very important. Now let's go to decay series. Decay series. The decay series is simply a series of disintegration that occurs when a natural or an artificial radioactive element undergoes chains of disintegration to get a final nuclide. You refer to as a decay series. A particular radioactive substance, it can be artificial, it can be natural. It keeps decaying and decaying and decaying and decaying and decaying and decaying. The initial compound or the initial substance is called the parent compound, while the final substance it will get to is called the terminal compound, okay, or the terminal nuclide, as the case may be. Now, that process whereby one particular substance will undergo multiple decay involving beta, alpha, beta, alpha, beta, alpha, beta, alpha, and ends with a particular element. That process is referred to as a decay series, okay? And typical examples of elements that can do that, we have uranium, we have thorium, we have neptunium, and just many of them like that. Uranium, for example, will undergo 19 decays to to lead to lead-208. It is called the uranium series, which we're going to see as time goes on. Now, during the disintegration, it may interest you to hear that new elements are going to be formed. And this new element cuts across alkali metals, alkali earth metals, boron family, carbon family, pneumogens, chalcogens, halogens, even noble gases are formed. So it is an important decay in chemistry. Very, very important and key. However, these elements undergo such series of decay either occurs naturally or artificially. Now, the natural ones are as old as creation. These elements that can undergo such decay, as I said before, the ones that are natural ones, they are as old as creation. For example, uranium, thorium. Those ones are as old as creation. Uranium, for example, has a half-life of about 4.5 billion years. That is uranium 235. And then thorium 232 has a half-life of about 14 billion years. Uranium 238, a half-life of about 4.5 billion years. They are actually called nuclides because they have no charge, and have a fixed atomic mass and a fixed mass number. That is why you call them nuclides. Fixed atomic mass and fixed mass number. That is why you call them nuclides. Okay, very, very important. So that takes us into the three basic type of naturally occurring series. We have three series that occur naturally and one that occurs artificially, which we are going to see. The three series that occur naturally are the actinium series, the uranium series, and the thorium series. The only one that occurs artificially is the Neptunian series. You have to remember this, guys. Very important. So let's kick off with the first one there, which is the actinium series. Now, the actinium series has a parent nuclide of uranium-235. So uranium-235 will undergo a total of 17 disintegrations. When we mean 17 disintegration, it will start by decaying through alpha to give you thorium. The thorium will decay through beta to give you potassium. Potassium will decay through alpha to give you actinium. Actinium will experience two decays, a beta decay to give you thorium, an alpha decay to give you francium, and then francium will undergo two decays, alpha decay to give you actinium, and then a beta decay to give you radium. Radium will undergo alpha decay to give you radon. Radon will undergo alpha decay to give you polonium. Polonium will undergo beta decay to give you bismuth. Polonium will undergo alpha decay again to give you this. So it will undergo so many decays, and at the end of the day, it will land with lead 207. So it has its parent nuclide as uranium-235, and however, a final or a terminal nuclide as lead-207. The actinium series belongs to the 4n plus 3 series. Why? Simply because the final nuclide will leave a remainder of 3 when divisible by 4. If you try to divide 207 by 4, you will discover that you will have a remainder of 3. So it is 4n plus 3 series. Okay, good. So that takes us to the second series there, which is the uranium series. The first one was actinium. Good. Now the uranium series has its nuclide parent as uranium-238. Take note, there's a difference. Actinium series is uranium-235. As for the uranium series, is the uranium-238 as the parent nuclide. And this will undergo a total of 19 disintegration, including the parent, to lead to a final nuclide of lead-206 as the mass. And of course, this belongs to the 4n plus 2 series because the final nuclide, when divided by 4, will leave a remainder of 2. You get it? Very important. So the key things you need to know here are the parent nuclide and the terminal nuclide. The parent nuclide is uranium-238, the terminal nuclide is 206. As for the actinium series, the parent nuclide is 235, the final nuclide is 207. So that takes us to the last naturally occurring series, which is the thorium series. As for the thorium series, it has a parent nuclide of thorium-232, just like the name implies, thorium-232, not 234. Take note because there is a discrepancy. thorium naturally occurs as 234. So everybody feels like it's actually 234. No, it's thorium 232, and it undergoes 12 disintegrations to have its final nuclide as lead 208. And of course, if you remember, this belongs to the 4N series, no remainder. Why? Because no remainder is left when divisible by 4. So 208 divided by 4 is a perfect multiple of 4. So it's 4N series. And that is the thorium, okay? From lead 2, so from thorium 232 to lead 208, leading to the production of many elements, noble gases, halogens inclusive. So that takes us to the last one, which is the artificially occurring series, which is the Neptunian series. This is not a naturally occurring series. Its parent nuclide is Neptunian 237 and undergoes a total of 14 disintegrations to yield a final nuclide called bismuth 209, and belongs to the 4N plus 1 series because when the mass of bismuth, which is 209, is divided by 4, it will leave a remainder of 1. So it belongs to the 4N plus 1 series. Very important. Parent nuclei, Neptunian 237, terminal nuclide, bismuth 209. So you got to remember this, and that is that for the case series. And that takes us into nuclear fission and nuclear fusion. Nuclear fission has to do with splitting of one heavy nuclide into two or more smaller nuclides with a huge amount of energy being released. A neutron particle is usually used to bring about this splitting because of its high penetrating power compared to other particles. Take, for example, one neutron particle is used to split uranium-235. And when it does that, once it absorbs a neutron, the mass will increase from uranium-235 to uranium-236, which is highly unstable. So it will split into two, which are barium and krypton-36. Barium-56, krypton-36. And when that happens, the masses of barium is 141, that of krypton is 92. And when that happens, 3 new neutrons are formed in the process, and a very huge amount of energy is released, which is about 200 mega electron volts. So this is what we call nuclear fission. This type of nuclear reaction is applicable in the creation of atomic bombs. Oh yes, and in nuclear reactors, a nuclear reactor is a way of creating electrical energy, making use of radioactive substances. Okay, good. So it is used in nuclear reactors to slow down the speed of electrons. Very important. So that takes us to nuclear fission. Nuclear fission is just the reverse of nuclear fission. Nuclear fusion involves the fusing or the joining together of heavy nuclei to form one large nucleus, together with a very big amount of energy release. For example, you take deuterium plus tritium, join them together to form helium. That is what we call nuclear fusion. Of course, plus a neutron will be formed and a high amount of energy will be released. Or you take 2 deuterium particles to form one helium nuclei. So, and a very high amount of energy will also be released in the process. All right. So, but take note, the helium here has a mass of 3. Yeah. So as to counterbalance with the neutron emitted to make it 4 on the reactant and 4 on the product. Applications. Now, nuclear fusion is used in the production of hydrogen nuclear bomb. It is also used by the sun to produce solar energy, aka stellar energy. And in the production of this energy, you find 4 atoms of hydrogen, which are actually called protium, combining together to give you a helium nuclei plus 2 positrons and 1 big energy release in the process. 1 big energy is released in the process. Now, application of radioactivity in general. Number 1, it is used in treating cancer. It is also used in carbon dating. Okay, it's used in treating cancer. Yeah, perfect. Then carbon dating. Now, as for carbon dating, that's a topic on its own. So I want to discuss what carbon dating is all about. it's important for you to first know that carbon exists in three isotopic forms, which are carbon 12, carbon 13, and carbon 14. Now, the only radioactive isotopic form of carbon is carbon 14, right? Good. Now, carbon 14 is actually formed when cosmic rays strikes nitrogen in the atmosphere. So if you have nitrogen plus a neutron, it will give you carbon 14 and a proton, which is hydrogen atom. Now, this carbon 14 formed is absorbed by plants and animals, and at that, carbon 14 begins to undergo a beta decay to release neutrons. That means once plants and animals take this carbon 14 into their system, animals, plants will definitely receive them through sunlight, for them to manufacture their food through photosynthesis, they have to do that through sunlight. So they absorb carbon 14 in them, and then animals that feed on green plants and us as human beings also will absorb that into our body system. Now, as soon as the animal or the plant dies, what happens? The carbon 14 begins to undergo a beta decay. That means it will emit an electron to go back to nitrogen. Carbon 14 has a half-life of approximately 5,730 years and decreases by 50% of its original content after 5,750 years. The age of a long-death decay substance can be predicted by the use of a mass spectrometer. What it does is to simply detect the amount of carbon 14 present in that particular dead decayed substance, and through that percentage, calculate the number of half-life that has passed to know the current age of that substance. If you pick a dead decay bone, maybe deep from the ground, and take it to a mass spectrometer, and the mass spectrometer detects it as 2.5% of carbon 14 inside, all you need to do is to calculate the amount of half-lives that have taken place from 100%, because as soon as everybody dies, the carbon 14 content in them is 100%. So divide 100% into 2, you get 50%. Divide it again, you get 25%. Divide it again until you get to 2.5. Count the number of half-life, multiply by 5,730 years, and that will tell you how long that substance has been on the ground. And it's important for you to know that carbon 14 has a maximum accuracy of 50,000 years. Any object that has gone beyond 50,000 years, carbon 14 will be deficient in giving you accurate values. That is a fact. And on that note, you may need to fall back to naturally radioactive substances that have a higher half-lives to be able to determine anything that is above 50 years. And a typical example is uranium-238 that has a half-life of about 4.5 billion years, as old as the creation of mankind. Potassium-40 that has a half-life of about 1.25 billion years, Alright, that takes us to balancing of nuclear reaction. How do you balance nuclear reaction? It's a very simple process, just 3 steps. Number 1, ensure that the number of charges on both sides of the reaction are equal. Number 2, ensure that their masses on both sides of the reaction are also equal. And then number 3, in the presence of a molecule, of a mole, maybe 2 radon or 2 electron or 2 beta particle, as the case may be, in the presence of a mole in front of a particle or an element, multiply that number of moles by the charge, and also multiply that number of moles by the mass. Remember, the mass is always at the top while the charge is at the bottom. Multiply that to get the exact quantity of charge on mass on either the reactant and the product, and perform your balance reaction properly. And so that takes us to the calculations of radioactivity, and we go into the facts properly. Number 1, the half-life of a radioactive isotope is the time taken for half of the initial amount of that substance to decay. And this is given by half-life, which is 0.693 all over alpha. Not really alpha, it's actually gamma. And that gamma there stands for the decay constant, or the disintegration constant, or the transformation constant, or even at times it is called the radioactive constant. And it is always measured in per second, per years, depending on the way the question is being asked. The 0.693 is actually ln 2. Okay, so you have to take note of that. Then secondly, the fraction left of a radioactive isotope after a given period of time to decay is given by F left, which is 2 raised to power minus n. What does that n stand for? Number of half-lives. And what is the number of half-life? The number of half-life of a radioactive isotope is simply the time taken all over the half-life. So it's simply Tn all over the half-life. It's important for you to note that the algebraic sum of the fraction left and the fraction lost of a radioactive isotope after a period of n decay is equal to 1. Fraction lost plus fraction left is equal to 1. And that simply means that fraction loss can be calculated by looking for 1 minus fraction left. And remember, fraction left is 2 raised to the power minus n, and n is equal to t all over t half-life, right? Next, the relationship between the initial amount, the final amount, or the final quantity, the initial quantity, and the number of half-lives of a radioactive isotope is simply Ni all over Nf equals 2 raised to the power n. Ni is the initial amount, initial count, it can be anything. Nf is the final count, okay? While 2 raised to the power n, the n there stands for the number of half-lives, which we have done before. Now it is pertinent for you to know that the initial amount must always be greater than the final amount. Why? Because disintegration will definitely take place. It starts disintegrating from initial, final must be small. You get it? If you don't get it, forget about it. Next is activity. Activity is simply the rate at which a substance decays spontaneously. That is all. What is the rate at which a particular substance decays? You refer to it as activity. Now, there is what we also call specific activity. Now, you are specific about the mass being decayed. So, specific activity is simply the rate at which 1 gram of a substance disintegrates spontaneously. You get the difference? Activity is simply the rate at which disintegration occurs. But as for specific activity, it is the rate at which 1 gram of that substance disintegrates spontaneously. Now, what is the formula for activity? It is simply lambda times the Avogadro's number times the mass, which is not specified, all over the atomic mass. While specific activity is simply lambda times the Avogadro's number all over the atomic mass. Now, the difference between these two formulae is just mass. Here, the mass is 1. And take note, your mass is always in grams, okay? Specific activity can also be determined by dividing the activity by the mass. So that will also give you specific activity. So I think basically that is that the lambda there simply stands for decay constant, okay? Very important, decay constant. And specific activity is measured in disintegration per second per gram. Very, very important. So you should always remember that. And it's also important for you to know that 1 becquerel is equivalent to 1 disintegration per second. 1 Curie is 3.7 times 10 raised to the power 10 disintegration per second. 1 millicurie is 3.7 times 10 raised to the power 7 disintegration per second. 1 microcurie is 3.7 times 10 raised to the power 4 disintegration per second. And 1 nanocurie is 37 dps, okay? Very important. And that takes us and launches us into the last part of nuclear chemistry, which is binding energy. What is binding energy? This is the smallest amount of energy required, not to bind, not to bring together, but to split the nucleus of an atom into constituent nucleons. The smallest amount of energy required to split the nucleus that is made up of proton and neutron into protons and neutrons is referred to as binding energy. Nucleons are the components of the nucleus, okay? Good. Now, when the nucleus of an atom splits, The mass before and the mass after the splitting are not the same. In fact, for a matter of fact, the mass after the splitting is always greater than the mass before the splitting. Why? This is because part of the energy absorbed during the splitting is converted to energy, is converted to mass, which makes the mass after the splitting heavier. And therefore, if you find M2 minus M1, which is the mass after the splitting, minus the initial mass, what it will give you is called the mass defect. And that mass defect, by the time you multiply it by the square of time, it gives you what we call binding energy. And that is Albert Einstein's formula. Okay? So that is the binding energy per nucleus. If, however, you want to calculate the binding energy per nucleon, then you will have to divide that binding energy by the number of nucleons, which is equivalent to the mass of the atom. I'll give you an example. Helium. Helium has 2 protons and 2 neutrons inside its nucleus. If the binding energy of helium is 1000, the binding energy per nucleon will be 250. Why? Because it's going to be 1000 divided by 4. The 4 signifies the 2 protons and 2 neutrons to give you 250. So it is a fact for you to know that the binding energy and the binding energy per nucleon, binding energy is always greater than the binding energy per nucleon. Very important. Binding energy per nucleon is the energy required to break one of the nucleons out of the nucleus, which is 250 if the total binding energy is 1000. All right, so that takes us to another amazing part. It is important for you to also know that one atomic mass unit, or that is 1 AMU, is equivalent to 931.5 mega electron volts. 1 U, which is unified, U stands for unified atomic mass, okay? 1 U is equal to 931.5 mega electron volts. And then 1 atomic mass unit is also equivalent to 1.66 times 10 raised to the power minus 27 kg, assuming you want to convert it to kg, okay? And then 931.5 mega electron volt is also equivalent to that amount. Now, if you want to convert from AMU directly, you want to convert it directly into joules, all you need to do is to multiply it by 1.6 times 10 raised to the power minus 27 kg. And that will give you your value in joules, right? If you want to convert it to mega electron volt, because your calculations is in mega electron volt, all you need to do, multiply your AMU by 931.5 mega electron volts, and your answer will be in mega electron volts. Binding energy is mass defect times the square of light. And mass defect is the change in the mass of the nucleus and the mass of the particles. The mass of the nucleus comprises the mass of the proton and the mass of the neutron. The mass of the nucleus can also be obtained by mass of the atom minus the mass of the electron. These are key words. These are key facts which you have to remember. Thank you for listening. This is the end of Chem 111. Wish you all the best, and boom, you're good to go.